I want to begin with a confession. For most of my career, when students or journalists or curious people at dinner parties asked me whether time travel to the past was possible, I gave the careful, responsible, thoroughly hedged answer that most physicists give. I said something like, well, the equations permit certain solutions that look like closed, timelike curves, but the physical realizability of those solutions is another question entirely, and there are good reasons to think that nature conspires to prevent them, and in any case, we have never observed anything that looks like a signal from the future, and so the practical answer is probably no. That answer is true as far as it goes. But I have come to think it is not the most honest answer, and the reason I have come to think that is that it treats time travel as an exotic, speculative, possibly forbidden phenomenon that lives at the outermost margins of what physics allows. Whereas the more carefully I look at what the equations actually say, the more I think that framing is backwards. Time travel to the past is not a marginal possibility that the equations barely tolerate and that nature probably forbids. It is a geometric feature of space-time that is already present in our best theories, that does not require exotic matter or wormholes or any technology beyond a sufficiently curved space-time, and that is prevented in the situations we encounter, not because the physics outlaws it, but because the conditions required to make it happen are extremely difficult to achieve, and because we happen to live in a region of the universe where space-time curvature is modest. Under one specific condition, a condition that the mathematics of general relativity describes with complete precision, time travel to the past is not just possible, it is inevitable. It is what the geometry of space-time demands. That condition is a closed, timelike curve. I am going to explain what that means with the care it deserves, because the phrase sounds technical in a way that obscures what it is actually saying, which is something geometrically clean and physically profound. But before I get to the mathematics, I want to set the stage by telling you about the person who first found this solution and what it cost him to find it. Kurt Gödel was one of the greatest logicians and mathematicians of the 20th century. You may know his name from the incompleteness theorems. The stunning results he proved in 1931, showing that any sufficiently powerful formal mathematical system contains true statements that cannot be proven within that system. Gödel essentially showed that mathematics is inexhaustibly deeper than any attempt to axiomatize it completely, that truth outruns proof, that the map can never be the territory. It is among the most profound results in the history of human thought. Gödel spent the later part of his career at the Institute for Advanced Study in Princeton, where he was a close friend and daily walking companion of Albert Einstein. Their friendship was one of the intellectual marvels of the 20th century. Two of the greatest minds in the history of science, walking together through the streets of Princeton, talking about physics and mathematics and the nature of reality. Einstein said once that in his later years, his own work did not mean much to him, and that he went to the Institute mainly for the privilege of walking home with Gödel. In 1949, Gödel published a paper that he had prepared as a birthday gift for Einstein. The paper contained an exact solution to Einstein's field equations of general relativity, a valid description of a universe that is consistent with every requirement the equations impose. The solution described a rotating universe, a cosmos in which the matter content is spinning. And Gödel showed that in such a universe, space-time is curved in a way that permits, and in fact demands, the existence of closed time-like curves, paths through space-time that are physically traversable, that always move locally forward in time as measured by a traveler on the path, but that curve back and close on themselves, returning to their own past. Einstein's reaction to Gödel's solution was deeply interesting. He acknowledged that the solution was mathematically valid. He could not find any flaw in the derivation, but he was deeply troubled by it because the existence of closed time-like curves seemed to violate something that Einstein felt should be a fundamental requirement of any physical theory, the impossibility of influencing your own past. He spent considerable time trying to find a physical argument that would rule out Gödel's solution, and he was never fully satisfied with the arguments he found. The reason Einstein's discomfort matters is not that Einstein was always right. He was not. His instinct against quantum mechanics, his resistance to the Copenhagen interpretation, turned out to be wrong in important ways. His discomfort with closed timelike curves might be similarly wrong, but it matters because Einstein understood general relativity as well as anyone who has ever lived, and his inability to decisively rule out Gödel's solution is itself significant. The solution is there. It is valid. It is a legitimate solution to the field equations, and the field equations are our best description of how space-time works. Now let me take you through the geometry, because I want you to understand what a closed timelike curve actually is, at the level of the mathematics, not just as an analogy. In general relativity, space-time is a four-dimensional manifold equipped with a metric, a mathematical object that tells you the distance between nearby points. The metric encodes the geometry of space-time, including the effects of gravity and, critically for our purposes, the causal structure. At every point in space-time, the metric defines what are called light cones. The future light cone at a point consists of all the paths that a light signal emitted from that point can take. The past light cone consists of all the paths from which a light signal could have reached that point. The interior of the future light cone is the region that can be causally influenced by events at that point. The interior of the past light cone is the region that could have causally influenced events at that point. A timelike curve is a path through space-time that always stays within the light cones. It is a path that a massive object could follow, moving always slower than light, always locally forward in time. The world line of any ordinary object, your world line through space-time from your birth to your death, is a timelike curve. It never crosses outside the light cones. It always moves into the local future at every point along its length. A closed timelike curve is a timelike curve that closes on itself. It is a loop. The path goes forward in time at every local moment, moving always within the light cones, but it curves through space-time in such a way that it eventually returns to its own starting point. A traveler following a closed timelike curve would experience continuous forward motion in their proper time, would feel no violation of the local laws of physics at any moment, would never feel themselves moving backwards in time, but would eventually find themselves back at the same event in space-time that they started from in their past, at a moment before they began the journey. The word inevitable in my title is doing specific work here, and I want to be precise about what I mean by it. In Gödel's rotating universe, closed timelike curves are not just possible, they are geometrically required. Every event in the space-time has a closed timelike curve passing through it. There is no point in the Gödel universe where you cannot, in principle, construct a path through space-time that returns to the past. The geometry of the rotating cosmos makes the past accessible everywhere and always. This is not a quirk of one exotic solution. Closed timelike curves appear in many other solutions to Einstein's equations. They appear in the Kerr metric, which describes the space-time around a rotating black hole. They appear in certain cosmological solutions with exotic matter distributions. They appear in the traversable wormhole solutions discussed by Kip Thorne and his collaborators in the late 1980s. They appear in the Van Stockham solution for a rotating dust cylinder, in the Tipler cylinder, in the Morris-Thorne wormhole. The equations keep producing them. Solutions that satisfy every mathematical requirement keep containing them. General relativity, as a mathematical theory, has no built-in mechanism that forbids them. They are part of the theory's solution space, and the solution space is what the theory describes. Now, I want to address the most serious objection to taking closed timelike curves seriously as physical possibilities. The objection is not mathematical. It is physical and philosophical. It is the problem of causality violations, and it is a real problem that deserves to be taken seriously. If closed timelike curves exist, then a traveler following one could return to their own past. And if they could return to their own past, they could influence events in ways that would change their own history. The grandfather paradox is the most vivid version of this. If you travel back in time and prevent your grandfather from meeting your grandmother, you prevent your own birth, which means you never travel back in time, which means your grandfather does meet your grandmother, which means you are born, which means you do travel back, which means you prevent the meeting, and so on, without resolution. A logical contradiction with no consistent solution. This paradox is real. It is not a failure of imagination or a misunderstanding of time travel. It is a genuine logical problem with histories that are not self-consistent. And it has led many physicists, including Stephen Hawking, to propose what Hawking called the Chronology Protection Conjecture, the idea that nature always conspires to prevent the formation of closed time-like curves, that quantum effects will always disrupt the space-time geometry before a closed time-like curve can form, that the universe is, in some deep sense, protecting the consistency of its own history. Hawking's conjecture is an attempt to take the mathematical possibility of closed time-like curves and argue that physics, specifically quantum effects in curved space-time, will always intervene to prevent them from actually forming. He did specific calculations suggesting that quantum vacuum fluctuations would diverge to infinite energy density at the point where a closed time-like curve would form, essentially destroying the space-time geometry before the time machine could become operational. This is a serious argument made by a serious physicist, and it cannot be dismissed. But here is the thing about the chronology protection conjecture. It remains a conjecture. We do not have a complete theory of quantum gravity, and the calculations that Hawking and others did to support the conjecture were done in approximation schemes that break down precisely in the regime where they are most needed. The calculations show that quantum effects are important near the formation of a closed time-like curve. They do not definitively show that those effects always prevent the formation. Some calculations in other approximation schemes have found that the divergences are less severe than Hawking's calculations suggested, or that they occur in ways that might be compatible with the space-time remaining smooth. The honest answer is that we do not know whether the chronology protection conjecture is correct. We will not know until we have a complete theory of quantum gravity, which we do not yet have. Hawking himself acknowledged this. The conjecture is a bet about what that future theory will say, motivated by the intuition that closed time-like curves would create logical problems. It is not a proof. It is not a derived result. It is a reasoned expectation. Now let me tell you about the specific condition I mentioned in the title, because I want to be precise about what I mean by geometrically inevitable. The condition is this: sufficiently strong, sustained rotation of matter on a cosmic scale, combined with sufficient matter density, produces a space-time geometry in which the light cones tilt, not just curve, tilt. In the Gödel universe, the rotation of the entire matter content of the cosmos produces a global tilt of the light cones that wraps the future light cone around in a full circle. The result is that the future, after you travel far enough in space, points back toward the past, moving forward in time, locally, continuously, without ever reversing direction. You can return to your starting point in space-time. I want to make this concrete because the abstraction can obscure the physics. In flat space-time, the space-time of special relativity without gravity, The light cones at every point are tilted at exactly 45 degrees from the spatial directions. Future is up, past is down, and no matter how you move through space, you always move upward in time. You cannot reach your own past because the light cones everywhere point consistently away from it. Now introduce rotation. In a rotating space-time, the matter content drags space-time around with it, a phenomenon called frame dragging. Near a rotating mass, the space-time is twisted. The light cones at different points are tilted relative to each other by the rotation. The Kerr spacetime around a rotating black hole exhibits this, and in the extreme case of a maximally rotating black hole, the light cones inside the ergosphere are tilted so severely that even light cannot remain stationary in space. It is carried around by the rotation of the spacetime itself. Extend this to a cosmic scale. In Gödel's universe, the rotation is not of a single black hole, but of the entire matter content of the cosmos. The frame dragging effect is global rather than local. And the result of that global frame dragging is that at sufficiently large distances from any point, the light cones have tilted enough that their edges are pointing back toward the past. A path that starts at one event, moves outward in space through a series of locally future-pointing steps, can curve around and arrive back at the starting event. Not by moving backwards in time at any local moment, by taking a large enough detour through a space-time where the future direction is curved into a circle. The analogy I find most useful, imperfect as all analogies are, is a cone. If you draw lines on a flat piece of paper, they can never form a closed loop unless they intersect themselves. But if you wrap that paper into a cone, lines that were straight in the flat version can become closed loops on the cone. The local geometry of the lines has not changed. Each small piece of the line still looks straight, but the global geometry of the surface has made what was impossible on the flat plane inevitable on the cone. Closed timelike curves are the space-time analog. The local geometry of time is always pointing forward, but the global geometry of space-time in a sufficiently rotating universe bends the future back into the past. Do we live in a Gödel universe? Almost certainly not. The Gödel universe does not expand, and ours does. The Gödel universe rotates globally, and we have no evidence of a preferred axis of rotation in the large-scale structure of our universe. The Gödel solution is a valid mathematical solution to Einstein's equations, but it is almost certainly not the correct description of our universe. So the closed time-like curves in Gödel's solution do not directly threaten our everyday experience of causality. But this does not mean the lesson of Gödel's universe is irrelevant to ours. The lesson is about what general relativity permits when space-time is sufficiently curved and rotated, and our universe does contain objects with extremely curved, extremely rotating space-times, rotating black holes, rotating neutron stars. These are not as extreme as the Gödel universe, but they are objects for which the curvature and rotation of space-time are dramatic enough that questions about closed time-like curves are not purely academic. Let me tell you about the most concrete physical setting in which closed time-like curves might arise in our universe. The Kerr solution, the exact solution to Einstein's equations describing the space-time of a rotating black hole, contains a region called the ring singularity. The singularity of a rotating black hole is not a point as it is in the non-rotating Schwarzschild black hole, but a ring, a one-dimensional curve in space. And the mathematical analysis of the Kerr spacetime shows that the region near and through this ring contains closed time-like curves. To be precise, inside the inner event horizon of a Kerr black hole, the space-time geometry changes character in a way that is difficult to visualize. The radial direction, which outside the black hole is space-like, a direction in space, becomes time-like inside the outer horizon, as in the Schwarzschild case. But inside the inner horizon, something different happens. The radial direction flips back to space-like, and there are additional regions of space-time accessible through the ring singularity where closed timelike curves exist. I want to be honest about what this means physically. The inner structure of a Kerr black hole is mathematically described by the Kerr solution, but physicists are skeptical that the Kerr solution accurately describes the actual interior of real rotating black holes. The reason is that the interior of a black hole is subject to instabilities, to quantum effects, and to effects of infalling matter that the idealized Kerr solution ignores. The full picture of what happens inside a rotating black hole's inner horizon is one of the deepest open questions in classical and quantum gravity. The closed timelike curves in the Kerr solution may be a mathematical artifact of the idealization rather than a feature of physical black holes, or they may not be. We do not know. There is a related possibility that has been explored more seriously as a potential physical mechanism for closed timelike curves: traversable wormholes. A wormhole, in the general relativistic sense, is a topological handle in spacetime, a tunnel connecting two distant regions. Einstein and Rosen noticed the possibility in 1935, though the Einstein-Rosen bridge they described was not traversable. In 1988, Kip Thorne and his collaborators showed that if you allow for matter with negative energy density, what physicists call exotic matter, you can construct a wormhole that is stable enough to traverse. And in 1991, Richard Gott showed that if you allow two traversable wormholes to move relative to each other in specific ways, or if you allow one mouth of a traversable wormhole to undergo time dilation relative to the other, you can turn the wormhole into a time machine, a device for sending signals or travelers to the past. The catch, as always, is the exotic matter. Matter with negative energy density does not exist in the form required by the wormhole solution. Quantum field theory allows for small regions of negative energy density, the Casimir effect being the most familiar example, but not the sustained macroscopic negative energy density required to keep a wormhole open. This is probably the most serious practical obstacle to wormhole-based time travel, more serious even than the energy requirements. We do not know of any physical mechanism that could produce the required exotic matter at the required scale. But I want to note something that I think is important and that often gets lost in discussions of these practical obstacles. The obstacles are practical, not fundamental. The physics does not say that exotic matter is impossible in principle. It says we do not know how to make it and have not observed it in the required form. That is a very different thing. The history of physics is full of materials and phenomena that were considered practically impossible and turned out to be achievable once the right conditions and techniques were found. Superconductivity was considered impractical for applications until the discovery of high-temperature superconductors. Bose-Einstein condensates were considered a theoretical curiosity until they were created in the laboratory. The practical impossibility of exotic matter is a serious constraint on near-term time machine construction. It is not a fundamental prohibition built into the laws of physics. There is one more approach to closed timelike curves that I want to tell you about because it is perhaps the most mathematically elegant and because it connects to ideas in physics that go well beyond the question of time travel. It involves cosmic strings. Cosmic strings, if they exist, are one-dimensional topological defects in space-time, hypothetical structures formed in the early universe during phase transitions in the fundamental fields. They are not strings in the string theory sense. They are more like cracks in a crystal, places where a field that fills the universe became misaligned as the universe cooled, forming linear structures with enormous energy density per unit length. The energy density of a cosmic string could be as high as 10 to the 22 kilograms per meter, roughly the mass of a mountain compressed into every centimeter of length. They have never been directly observed, and there are constraints from the cosmic microwave background and gravitational wave searches that limit their abundance, but they are not ruled out. In 1991, Richard Gott showed that two cosmic strings moving past each other in opposite directions at sufficiently high velocities would produce closed time-like curves in the space-time around them. The geometry of the two moving strings creates a space-time in which, if you travel around the two strings in the right trajectory, you return to your starting point in space-time earlier than you left. The strings do not need to be exotic. They do not need negative energy density. They need only to be massive enough and moving fast enough relative to each other. Gott's model was immediately subjected to intense scrutiny. Stephen Hawking and others argued that you could not create the two-string configuration without starting with more energy than the total mass energy of the observable universe, which effectively rules it out as a practical mechanism. The critique is serious and probably correct as a practical matter, but the mathematical solution is valid. Two sufficiently massive, sufficiently fast-moving cosmic strings produce closed time-like curves. The geometry demands it. No exotic matter required. No violations of the known energy conditions. Just strings and velocity and the curved geometry of space-time. What I want to draw from all of this, from Gödel's rotating universe to the Kerr-ring singularity to traversable wormholes to Gott's cosmic strings, is a picture that I think is more accurate than the one usually presented. Time travel to the past is not an idea on the fringe of physics. It is not something that physicists reluctantly acknowledge as a mathematical oddity before dismissing it as physically irrelevant. It is something that appears repeatedly in multiple independent solutions to our best equations, in multiple different physical settings, with multiple different mechanisms. The equations keep producing it. The geometry of space-time, when sufficiently curved and rotated and topologically modified, keeps generating it. General relativity, as a mathematical theory, finds closed, time-like curves completely unremarkable. They are part of the landscape of solutions. What physics has not settled is whether our particular universe, with its particular matter content and its particular history and its particular quantum properties, permits the formation of closed, time-like curves under any physically achievable conditions. The Chronology Protection Conjecture says no, and there are serious arguments in its favor. But it remains a conjecture. The question is open. And the condition I described in the title, the geometric condition under which time travel to the past is inevitable, is sufficient rotation combined with sufficient curvature. That is the condition. Not exotic matter, not wormholes, not any technology, just rotation and curvature taken to sufficient extremes. The Gödel universe satisfies it globally and makes closed time-like curves everywhere. The Kerr solution satisfies it locally near the ring singularity. The Gott model satisfies it in the neighborhood of two fast-moving massive strings. In each case, the geometry does not merely allow the past to be accessible, it demands it. The closed time-like curves are not optional features of those spacetimes. They are inevitable consequences of the geometry. That is what I mean by geometrically inevitable under one condition. I want to close with something that I think is more important than the question of whether time machines can be built. More important because it is about what the existence of these solutions tells us about the nature of time itself. We began this conversation with the assumption that time has a direction, that the past is categorically different from the future, that the sequence of events in a history is fixed and irreversible. That causality, the principle that causes precede effects, is a fundamental law of nature. These assumptions feel so basic that questioning them seems almost incoherent. They are baked into the language we use to describe the world, into every sentence that has a subject and a verb and an object, into every story that has a beginning and a middle and an end. The solutions I've described today are not just exotic mathematical curiosities. They are telling us that these assumptions, deep as they are not fundamental features of the laws of physics. General relativity does not contain a direction of time. Einstein's equations are time symmetric. They work equally well in both temporal directions. The solutions to those equations include spacetimes, in which there is no consistent global notion of before and after. Gödel's universe has no well-defined cosmic time. It has no global foliation into past and future. The question of whether event A happened before or after event B has no answer in Gödel's spacetime that is independent of the path you take between them. The arrow of time, the directionality that feels so fundamental to our experience, is not a feature of the fundamental equations. It is an emergent property of the particular initial conditions of our universe, of the extraordinarily low entropy state from which the Big Bang arose, of the thermodynamic processes that have been running ever since. It is real, it is important, but it is not fundamental in the way we assume it is. It is a property of our particular solution to the equations, not a property of the equations themselves. And that means that the equations are telling us something about the deep nature of time that our experience systematically conceals from us. Time is a dimension. It has a direction in our universe because of contingent facts about our initial conditions. But it does not have to have a direction. There are valid solutions to our best equations, valid descriptions of possible universes in which time does not have a direction, in which the past can be revisited, in which closed time-like curves make the geometry of history more like a tangle than a line. We do not live in one of those universes, almost certainly. But we live in a universe whose physics permits those universes to be described, whose equations have those solutions, whose geometry can accommodate those possibilities. And knowing that changes the question from can we go back to what does it mean that we cannot? What is it about our specific universe, our specific initial conditions, our specific matter content that prevents the curvature and rotation from reaching the threshold at which time bends back on itself? That question, I think, is one of the most interesting questions in all of physics. Not because it promises time machines in the near future. It does not. But because the answer to it will tell us something deep about why our universe has the particular character it has, why time flows the way it does, why the past is inaccessible in a cosmos where the geometry could, in principle, have made it otherwise. Time travel to the past is not impossible. It is geometrically inevitable under one condition, and the condition being unfulfilled in our corner of the universe is not a law, but a fact. A contingent, explicable, physically interesting fact that our best theories have barely begun to illuminate. If any of this changes how you think about time, about causality, about why the future feels open and the past feels closed, I want to hear it in the comments. Tell me which of these solutions you find most physically plausible and why. Tell me what you think the Chronology Protection Conjecture gets right and what it might be missing. And subscribe if you want to keep going deeper into the places where the physics of space-time leads to questions that most people are afraid to ask out loud.